Okay, in this video, we're going to go through section 5.2, which is on the definite integral. All right, so the previous two videos were the introduction to integration. There was an introduction to integration part 1 and a part 2. So that's how we started calculus 2, integral calculus. We were introduced to integration, and that's when we went through section 5.1. But then in part 2, we came to the beginning of section 5.2, which gives the official definition of what an integral is. And so we talked about what exactly does an integral mean? What does integration mean? We talked about what's the difference between a definite integral and an indefinite integral. Why is anti-differentiation, why is that called integration? Why do people call it integration? What does this symbol mean? This integration symbol. Okay, and now in this video, we're going to actually go through section 5.2, the entire section. All right, and section 5.2, as you can see, is on the definite integral. Okay, now, as we talked about in the previous video, the introduction to integration part 2, the definite integral is really, you can think about it as it's everything that we did in section 5.1. So in section 5.1, we developed a method for finding the area under a curve using an infinite sum of rectangles. That's a definite integral. All right, so definitely you need to at least go watch the previous video, the introduction to integration part 2, where I really go through the start of this section 5.2 in detail. You need to watch that before watching this video. You don't have to watch the introduction to part 1 necessarily, but go watch the previous video where I go through this in detail. So we talk about how, in that video, we talk about how, so this is a definite integral. This is an indefinite integral. But as far as application goes, though, these are pretty different. These two are pretty different. This is associated with what we did in the previous section. This is like an infinite sum tool. And so the way we developed this was for finding the area under a curve with using an infinite sum of rectangles. But we're going to use this infinite sum tool. I'm calling it an infinite sum tool. I'm trying to get it separated from areas under curves, because we're going to use this tool to do for all kinds of different applications, like finding the length of a curve. If you've got a curve and you want to find its length, you can separate it up into tiny pieces and then sum the lengths of those tiny pieces, do an infinite sum, and get the length of the curve. That has nothing to do with areas, right? But we're still going to use this exact same definite integral tool to do that. This here, as far as application, it's not associated with infinite summing. Yes, mathematically, these are related, indefinite and definite integrals, through the fundamental theorem of calculus. And we'll talk about the fundamental theorem in the next section. But as far as application, this is just a symbol for saying antiderivative. Find the antiderivative of f of x. So we'll use this symbol for like in differential equations, or just, for any time you want to find the antiderivative. If you want to indicate find the antiderivative, you use this symbol. And again, I talk about in detail where all this comes from, why we do this in the previous video. Okay, but the point I'm trying to make is that in this section on the definite integral, we're focusing here. We're focusing on the infinite sum. We're not talking about this. Even though it looks like they're close to the same thing, we're not talking about this in this section. We're looking at the properties of the definite integral. And one of the main ways you differentiate this two is, as you can see, the limits of integration, the a to b. This doesn't have any limits. This does. That's the main way symbolically you differentiate between the definite and the indefinite integral. But again, as far as applications, you're not thinking about an infinite sum here. Everything we developed in the previous section, that whole idea of this infinite sum to find something, That's you don't, whenever you see an indefinite integral, you're not thinking about that. This is just a symbol for find the antiderivative of the function. That's it. This is not a symbol for find the antiderivative of a function. This is a symbol for this infinite summing tool. However, to solve this, we're going to see in the next section, we can solve this very easily without having to go through this whole summing process by finding the antiderivative. But that's just how you solve it. The antiderivative happens to be associated with solving this, and that's why this symbol is used for antiderivative. So again, we're analyzing the properties of, we're talking about this in this section. And before we get started, another thing to point out is that, so yes, really you look at this, you don't, in general, you should think about this as not an area calculation tool. You should think about this is like an infinite sum tool, an infinite summer. Even though we developed this from summing area for finding an area under a curve, as it mentions here, and as we're going to see in upcoming sections, with that in the length of the curve example, this is an infinite sum tool. You can use this for all kinds of things as an infinite sum tool. That's how you should think about it. However, as we go through this section in this video, we're going to analyze the properties of the definite integral through the lens of areas under curves. That's how you're mainly going to view the properties of this. That's how we developed it as far as finding the area under a curve. And that's how we're going to, when we go through this section, that's the main lens we're going to look at this through, the area under the curve lens. But just keep in mind, try and keep in mind, I know it's hard, that this is really an infinite summer. It's not an area under curve tool, it's an infinite sum tool. All right, so with that, as far as the definition of the definite integral and where the symbol comes from and the notation and all this, I went through all of this in detail in the previous video. We're going to start here. Note 2. The definite integral is a number. It does not depend on x. In fact, we could use any letter in place of x without changing the value of the integral. So that's something to note. We put the notation is we put the f of x dx, right? But it wouldn't, the way it works, and you get a better sense for this as we progress through the entire chapter, but you could replace x here with t. Like you couldn't do this. This is wrong. This doesn't make sense. But you could do this. You could change the variable to whatever you want, and that's the same integral. The integral doesn't. The variable doesn't change anything. Now, I guess in the context of the problem, if you give someone a problem and you give them a function of x, right? You give them some function of x, and then you right below you say, okay, I want the direct integral from a to b of f of t dt. Well, then they're not going to know what you're talking about, right? What are you talking about this function, right? But like they're just pointing out that what they're pointing out here is that you could have a function of x that's integrable, and you could evaluate the direct integral or the definite integral. You could take that exact same function and just change the variable to t and do the exact same definite integral, and you'll get the exact same answer. That's what they're saying. Okay, now the sum here, it says this occurs in definition 2, and it's called a Riemann sum. So what is this? This was if we come back, they're talking about this here. It's this portion of the infinite sum tool. It's this. So before you take you develop the sum, you're going to do the rectangle area sum procedure with like 50 rectangles or 10 rectangles or 100 rectangles. You can choose n. So you haven't taken the limit as n goes to infinity yet. It's just the sum with n number of rectangles. That they're calling that a Riemann sum. That's called a Riemann sum. And so what you can notice, what they're saying here is that what you can notice is that the definite integral of an integrable function can be approximated to with any desired degree of accuracy by a Riemann sum. So what a definite integral is so like if we look at this curve here, we know what a definite integral represents as far as the way we developed it is we're trying to find the area under this curve, right? And if you take the limit as n goes to infinity, you get the area. But if you're just looking at it from the perspective of the Riemann sum, so we're going to use, they have 1, 2, 3, 4, 5, 6, 7, like 8 rectangles. Well, what is this? This is an approximation for the integral, right? For the definite integral. That's what this is. That's how you can look at it. If you did 100 rectangles, you'd get a good approximation for the definite integral. So that's just something to note. We know that if f happens to be positive, then the Riemann sum can be interpreted as a sum of areas of approximating rectangles. Exactly. By comparing definition 2 with the definition of area in section 5.1, we see that the definite integral can be interpreted as the area under the curve. Okay, that's what I just said. Okay. If f takes on both positive and negative values, so what about this situation? Right? Up to this point, we've strictly been looking at a curve that's positive. Positive, and also the x's are positive as well. We've looked at that's the only scenario we've looked at. But let's keep the x's positive. But what about if some of the curve is negative? And so the way, as far as the definite integral, the way this works is it's going to be a net sum of areas. So you're going to add this area to this area and then subtract that area, and that's going to be the definite integral. It's the net area. And in fact, if we come up here, if you had a curve that went into the negative x region and you took the definite integral from a to b, it would just give you this area. What is this area here? It's a positive area. That's it. The fact that a is negative and b is positive doesn't change anything. Okay? And it would be the exact same idea if you had and you're going from here to here. It would be, so a is negative, b is positive, but it would just be the net area. You'd add this area and this area and this area, and then subtract from all that this area and this area, and it would be the net area. That would be the definite integral. Right, like if this is f of x, then the integral from a to b of f of x dx would be the net area. And it doesn't matter that a is negative, it's the same idea. Okay, so that's something to note. And as we learn other applications of the definite integral outside of areas under curves, you can use that same principle. It's going to be the net. It depends on the function you're integrating. What they're saying is that, even if the function doesn't we're not thinking about areas under curves, but if we're thinking about, lengths of a curve or whatever, if the function you're integrating in the integral ever goes negative, then it's going to be factored in as negative. It's going to be subtracted from the result. All right. Although we have defined the integral from a to b fx dx by dividing a to b into subintervals of equal width, there are situations in which it is advantageous to work with subintervals of unequal width. For instance, in exercise 5.1.16, NASA provided velocity data at times that were not equally spaced, but were still able to estimate the distance. We were still able to estimate the distance traveled. And there are methods for numerical integration that take advantage of unequal subintervals. Right, so numerical integration, that's when you're kind of doing a Riemann sum, like it's an approximate integration. And they're saying that there's methods for numerical integration that take advantage of unequal subintervals. If the subinterval widths are delta x1, delta x2, delta x to delta xn, we have to ensure that all these widths approach 0 in the limiting process. This happens if the largest width, max delta I approaches 0. So in this case, the definition of a definite integral becomes the limit as the max delta xi approaches 0. Yeah, so I mean, I'm not going to get into this too much. I mean, the definitions that we started with at the beginning of this chapter that have equal subinterval widths, that's what we're going to be. They're just mentioning this as a note, but we're going to be focusing on the definition of integration. This is the definition of the definite integral right here with equal subintervals. Okay, but they're just noting here that you can think about the idea of unequal subintervals, and in numerical integration you'll look at that. But as far as the definition of integration, we're not even going to think about this idea of unequal subintervals. Okay. Note 5. We have defined the definite integral for an integrable function, but not all functions are integrable. The following theorem shows that the most commonly occurring functions are in fact integrable. The theorem is proved in more advanced courses. So what does integrable mean? What did we see that integrable means? This means it's if this limit exists. If you set up this Riemann sum and you take the limit as n approaches infinity, if that limit exists, then the function is integrable. All right, so what functions are integrable? Let's take a look at this theorem here. If f is continuous on a to b, or if f has only a finite number of jump discontinuities, then f is integrable on ab. That is, the definite integral exists. So think about what this is saying here. If f is continuous, then as long as f is continuous on the interval you're analyzing, then the function is integrable. Well, that's interesting because, okay, I guess obviously if you have a function that's continuous and differentiable, nice and smooth, then it's integrable, okay? But we can have a continuous function that's not differentiable, right? There's a continuous function that's not differentiable. You got absolute values, continuous, not differentiable at a certain point. So, but they're saying, so like even with an absolute value, this is integrable, even though it's not differentiable here. The derivative doesn't exist here. They're saying this is differentiable. And furthermore, they're also saying that if you have a finite number of jump discontinuities, then it's also integrable. And this makes sense because what they're saying here is that, like, all right, if you have a jump discontinuity here, and well, actually, I'll do this. I'll make it non-differentiable there. Okay. If we want to find, so if we want to integrate from here to here, okay, they're saying this is integrable. And why does that make sense? Because, okay, well, we're just trying to find the area. This is the integral is going to be this, right? That's going to be the definite integral. They're saying finite number of jump discontinuities because, yeah, if you have like an infinite number of jump discontinuities or something, then, you know, that doesn't make sense. I don't know how you have an infinite number of jump discontinuities. That's just being mathematically, technically correct. But you can find this area, right? That's integrable. And I mean, even if you look at it from the standpoint of, you know, we've seen functions with jump discontinuities like the greatest integer function or whatever. So like, you know, it's something like, we've seen functions that look like this. Well, that's not differentiable. I mean, well, at least at the discontinuities, that's integrable. Could we integrate this? They're saying here that this is integrable. And why is it integrable? Because what's the integral going to be? It's going to be, if we're going from, okay, we're going from here to, we're integrating from here's A, here's B. What's the integral? Okay, this area plus this area plus this area, and then minus this area. So what they're saying here is that you would have to set up the Riemann sum And it might be, you might have to think a little bit just to get the Riemann sum set up correctly because of the discontinuities. But once you could set it up, even with the discontinuities, take the limit, and the limit would exist. Okay? And that's another thing I forgot to mention at the start of this video is that, so as we go through this section, some people might be coming back to this as a review. You might have already taken calculus and you're coming back to this as a review, this video. When you see, so if you might see a definite integral, okay? Let's go from 2 to 0 of square root of x dx. Okay, you see this and you're immediately thinking, okay, yeah, take the antiderivative of square root of x and then evaluate the antiderivative at 2 and subtract that from the antiderivative evaluated at 0. We have no idea. At this point, that hasn't been talked about yet. At this point in the textbook, we have no idea about how to evaluate a definite integral with an antiderivative at all. And in this entire section, we're not going to talk about that. Right now, the only thing we know, when we see this, the only thing we know is that, okay, I'm going to need to set up the Riemann sum as a function of n, so like n number of subintervals. I'm going to have to set up the Riemann sum for this function on the interval 0 to 2, and then once I get that Riemann sum set up, I take the limit as n approaches infinity, and that's what officially turns this into the definite integral. Okay, that's as of now, that's the only way we know how to evaluate this. Okay, so just keep that in mind. And that seems like a lot of work. Yeah, it is. But it's kind of like the definition of the limit. Once we learn the definition of the limit, that's the only way, at that point in the textbook, that's the only way we could evaluate derivatives, or the definition of the derivative. At that point in the textbook, that was the only way we could evaluate a derivative, is we had to do the full drawn-out limit definition. It wasn't until chapter 2 that we developed the techniques for making it a much quicker and easier process. Okay, so again, that's really important. Right now, when we see a definite integral like this, the only way we can evaluate this is, okay, I've got to set up the Riemann sum as a function of n for this function over this interval, and then when I take the limit as n approaches infinity of that Riemann sum, then that's when it turns into this definite integral, and that's how I can evaluate it. That's it. If f is integrable on a to b, then the limit in definition 2 exists and gives the same value no matter how we choose the sample points. That's right. Once you take the limit as n approaches infinity, then it doesn't matter if you choose the left endpoints, the right endpoints, the midpoints. To simplify the calculation of the integral, we often take the sample points to be the right endpoints. Then xi star is equal to xi, and the definition of an integral simplifies as follows. So what they're saying here is that what you probably noticed as we went through section 5.1, and I can come back here, okay? What we've talked about is that this is what we developed. It's this entire limit as n approaches infinity. We developed that in section 5.1. And it's just stating that once you take the limit as n approaches infinity of the Riemann sum, then this is the most general representation of section 5.1, because xi star, you can pick any point you want, and you're going to get the same, that the limit as n approaches infinity is going to be the same no matter what. So this is representative of the left endpoint Riemann sum, the right endpoint Riemann sum, the midpoint. This represents everything. That's why this is the most general way to summarize what we did in section 5.1. However, if you remember, the simplest Riemann sum to work with was the right endpoint Riemann sum. Why is that? Because if we come here, the way it's defined is that, so the endpoints of the subintervals are like, okay, so you're going from A to B. x0 is equal to A. x1 is equal to A plus delta x. x2 is equal to A plus 2 delta x. All the way up to xn is equal to b. That's the way it's set up. And so with that, if you're going to use a right endpoint Riemann sum, all you got to do is just put in. So for the first subinterval, you're just doing f of x1. That's the right endpoint. The second subinterval, f of x2. It gets a little more complicated if you're trying to do the left endpoint or the midpoint. The formula gets a little more complicated. The right endpoint is the simplest. And so what they're saying here is that because it's the simplest, the right endpoint, using the right endpoint Riemann sum is the simplest, and because when it comes to the definite integral, once you take the limit as integral goes to infinity, because it doesn't matter which points you choose, then you'll see in a lot of situations that the definition of the definite integral that's given is just based on the right endpoint method. So you don't have to do this big drawn out definition here. You could just say, you could just restrict it to using the right endpoint method and you get the same value regardless, right? This is simple. This is using the right endpoint method. They're saying, so the definite integral is equal to what? The limit as n approaches infinity of the sum from I is equal to 1 to n, just f of xi, where xi is a plus I delta x, and delta x is this. That's it. Boom, done. You see? Okay. So here they say express this as an integral. So they're saying write this like this. Write this as a definite integral. Write this in the integral notation. Okay. Now, if we compare these two forms, we can see that this is the same. This is the same form as this, and so from there, that you can just write. You see the f of x then is x cubed plus x sine of x, and so that's what they do. The interval is 0 to pi, so they go. The endpoints are 0 to pi. They put the integral symbol. The function, and this should be plus here, d of x, but the idea is just to point this out. In general, the way you would do this, if someone gives you this here, once you take the limit as n approaches infinity, again, it doesn't matter if you're using the right endpoint or the left endpoint. So you would look at you'd see the limit as n approaches infinity. Then you'd look at the Riemann sum and just make sure, okay, is this, as long as what they're doing is they're summing from I is equal to 1 to n, the function evaluated at any point within the interval. It doesn't matter. Here, it happens to be the right endpoint because we just discussed this theorem, but it doesn't have to be. As long as you see, okay, we're summing from I is equal to 1 to n, and it's some function evaluated at any point within each interval, and then times delta x. Well, then the limit as n approaches infinity of that is going to be the same no matter what left endpoint, right endpoint, whatever. Okay, but we can see this is a Riemann sum using right endpoints, but we're taking the limit as n approaches infinity, so it's just the definite integral. Okay, it says, later when we apply the definite integral to physical situations, it will be important to recognize limits of sums as integrals, as we did in example 1. So yeah, you want to be able to recognize these limits of sums here as integrals. When Leibniz chose the notation for an integral, he chose the ingredients as reminders of the limiting process. In general, when we write the limit as n approaches infinity of the sum from I is equal to 1 to n of f, the function evaluated at any point, delta x, is equal to this. What you're doing is, so when you do this, that's representative of this here. It's not just replacing the sum symbol. It has to be paired with the limit as n approaches infinity of the sum symbol. This means infinite sum, not just some infinite sum. So the limit as n approaches infinity from I is equal to 1 to n, then you can introduce this. All right. Now the limits of integration are just given in the problem statement. All right. Then you put the function that you're integrating, and then the delta x is replaced by dx because it's like dy dx. Okay, that's when you're going to infinity. It's like this is infinitesimally small. This dx, right? We know that's from differentiation. Well, that's what's happening. As n approaches infinity, the delta x is getting infinitesimally small. Right? Of course it is. And so that's why this becomes dx. Okay, now it says here evaluating integrals. And again, what are they talking about? They're talking about because if right now, if we're given any definite integral, we are only know how to evaluate this from the Riemann sum perspective. That's it. We have not talked about yet the idea of doing an antiderivative to solve this. That's not going to. We'll learn that once we learn the fundamental theorem of calculus. Right now in this section, we're solving this from the Riemann sum perspective, and so to be able to do that, what we're going to see in the upcoming example problems is we need to know how to work with summations. That's how you can solve this. And so they list out summation properties here to help you to solve this. So like the sum from I is equal to 1 to n of just I is equal to this. The sum from I is equal to 1 to n of I squared is equal to this. And I cubed is equal to this. And you'll see how this is helpful for evaluating these definite integrals from the summation perspective. And you might be wondering, well, where do these come from? Well, I get into this when we get to chapter 11, which was on infinite sums, infinite series. I'll talk about this, and I'll also talk about this at the end of the algebra playlist. We talk about summation properties and summation simplification. So I go into more detail on this at the end of the algebra playlist, and in chapter 11. I'll post a link to these videos in the description if you want to check it out. But you can see where these properties come from. And yeah, I talk about in those same videos, we talk about properties like this as well. So these are just summation properties that'll help you to. It's good to practice working with summations. So I don't want to overload you, but don't ignore this too much. You want to get good with working with summations because, again, in chapter 11, we're going to learn about infinite sequences and series, and so summations are a part of calculus, a part of math, and so it's easy to just ignore it because it's not one of the main subject topics in algebra or calculus, but you want to get pretty comfortable with summations. And so, but again, we're going to go through summations in a lot more detail in chapter 11 of Calculus 2. And also, it's also taught a lot in algebra. So we go into this in detail at the end of the algebra playlist as well. But I'll post links to those videos in the description. But yeah, so we're going to learn how to solve a definite integral with a much easier method in the upcoming sections. And so you're not always going to do the manual method. It's kind of like, again, finding a derivative using the definition of the derivative. Once you're done with calculus, you don't really do that ever anymore. You just use the quick methods to do it, right? And same idea here. Once we get through integration, you're not going to use this method to solve definite integrals. You're going to use the quicker method. But as far as it's good just for practicing, for understanding where this definition comes from, and good practice for working with summations. It's good to do some practice problems solving these using the manual method. And so to do that, you're going to want to reference these properties, and you'll see what I mean as we as we go through these examples, and once we work in the next video, work example problems. So, well, here's an example. So it says evaluate the Riemann sum for this function, taking the sample points to be right endpoints and going from a is equal to 0 to b is equal to 3 with n is equal to 6. Okay, so how do you do this? Well, all you're doing is you're separating, you're dividing 0 to 3 is 3 units. 3 divided by 6 is 1/2. So each interval is going to be 1/2 wide. They're going to be equally spaced, separated from 0 to 3 underneath the function or underneath or whatever. So if we look at the function, here it's above the function, here it's below, but it'll be these half. Each of these intervals is 1/2. Okay. Now, using the right endpoints, the idea is you're going to say, okay, what's the value of the function here? Multiply that times delta x. That's the area of this rectangle. What's the value of the function here, the right endpoint? multiply that by delta x. That's the value of this rectangle, because that's the area of that rectangle, because the function is going to be here, then here, then here. So that's the height of the rectangle. And you'll do the same thing all the way through, and you're going to add up those areas. And that's going to be the approximate net area. So this area minus this area. That's going to be an approximation for that using 6 rectangles, 6 intervals. Okay, but then it says now evaluate the actual integral. So it's the Riemann sum that you just did, but now you're taking it as instead of n is equal to 6, you're taking the limit as n goes to infinity. So how do you do this? Well, you just do this for n as a function of n. So instead of saying b minus a divided by 6, you just do b minus a divided by n. That's 3 divided by n. Okay? And then what you do is you see, okay, you kind of list out the right endpoints for x0, x1, x2, x3, and you come up with a formula, because the right endpoints are going to be, it's going to be some formula with an I in it, because you're summing from I is equal to 1 to n. So the right endpoints are 3i divided by n. Okay, where does that come from? It's for the right endpoints, so x0 is a. That's the left endpoint of the first subinterval. x1 is a plus delta x. Okay, well, a is, it gives us a is 0. A is 0. So x1 is a plus delta x, 0 plus 3 over n. x2 is a plus 2 delta x, so 6 over n. We're evaluating the function at x1, x2 at the right endpoints for each subinterval. So that's how you get the formula for xi. Because you're saying, like, okay, like it's the sum from I is equal to 1 to n, where I is the subinterval. You're going to be plugging in f of xi times delta x. And that's what they do here. 3i divided by n times 3 over n. But the limit as n goes to infinity. Now, you just have to evaluate the function, though, at 3i over n. So they plug 3i over n into, so into the function, f of 3i over n, they plug it in, okay? And then they get to this point. And it's once you get here, that's when you need the summation properties to help you solve it. This is where the summation properties come in. So they're gonna simplify this, and you can simplify it and get to this point. Now we have formulas for this sum and for this sum, right? The sum from I is equal to 1 to n of I cubed and sum of I equals 1 to n of I, and you can get all the way to this point here. And now this is a point where you can actually evaluate the limit using limit techniques as n approaches infinity. And there's the limit, and that's the integral. Okay, and so it's a negative because if we look here, it's a larger negative area than there is a positive area. So it's a net area. We can't interpret this. It's saying we can't interpret this as an actual area. It's a net area. Okay, and then here they do an illustration. They get the right endpoint Riemann sum and just plug in n is equal to 40, 100, 500, 1,000, 5,000. And here's with n is equal to 40. That's pretty good, right? With n is equal to 40, that's pretty good. Imagine n is equal to 1,000 or 5,000 or infinity. Okay, now it says here, we're going to work example problems, but you can look at a definite integral, and if you just graph the function over that interval, if you can find the area, then go ahead and get the area. And that's the definite integral. So what they're saying is, like, like here, well, we know how to find the area of triangles. So if this was x minus 1 dx from 3 to 0, so you could just evaluate the definite integral, just finding the areas. It's the area of this triangle minus the area of this triangle. And here, this is a curve, but we know this is a portion of a circle. And so you could find the area of a quarter circle, and that's the definite integral. It's just another perspective of looking at a definite integral. Since you know it's an area, and if you can use just regular geometry because of the function to find that area, then you could do it that way. Okay, the midpoint rule. We often choose the sample point to be the right endpoint of the ith subinterval because it is convenient for computing the limit. But if the purpose is to find an approximation to an integral, it is usually better to choose the xi star to be the midpoint of the interval, which we denote by x bar I. So what they're saying here is that for the infinite sum, for the definite integral, as we saw, it's convenient to use the right endpoint. And the main reason is because, like here, for this problem that we just did, if we didn't use the right endpoint, it would just make this math a little more complicated. That's what they're talking about. If you use the left endpoint or the midpoint, you could still do it, but it wouldn't be as clean. However, if what they're saying here is if you're actually trying to do an approximation, that's like what numerical integration is. You're doing an approximate integration. So in other words, like you're going to set up the Riemann sum and evaluate it. If we come here, you're going to set up the Riemann sum and evaluate it at n is equal to 500, and that's the integral. That you're taking that to be this is an approximation, right? It's an approximation. If you're not taking the limit as n goes to infinity, it's an approximation. Okay. What they're saying is if your intent is actually to do an approximation, then it's going to be more accurate in general to use the midpoint instead of like the right endpoint or the left endpoint. So that's what they give the midpoint rule here. And so you can see, yeah, you see how the xi is more complicated? 1/2 xi minus 1 plus x of I, as opposed to here, the right endpoint was just xi is the input. A plus I delta x. Here you got to incorporate xi and xi minus 1 with the 1/2. It's more complicated. Okay, properties of the definite integral. We're going to use these properties to solve definite integrals. And just note that even once we get to the fundamental theorem of calculus and we learn the simpler method for finding a definite integral, that we don't have to use the Riemann sums, we're still going to use these properties. These are properties of definite integrals in general, no matter how you're solving them. Okay, so that's important to note. Okay, I'm going to say that again. These properties here, even though we have no idea about how to solve the definite integral with using the antiderivative, the simple way, these properties still apply once we do learn that. So these properties you can always use to solve a definite integral if you're using, no matter what method you're using, if you're using the Riemann sum method or the actual official antiderivative simple method. Okay, so it says when we define the definite integral like this, we implicitly assume that a is less than b. But the definition as a limit of Riemann sums makes sense even if a is greater than b. Note that if we reverse a and b, then delta x changes from b minus a over n to a minus b over n. Therefore, if you have the exact same definite integral, but you just switch the positions of the limits of integration, then you just put a minus sign out front, right? So the definite integral from this is from b to a of f of x dx is equal to minus the integral from a to b of f of x dx. That's it. And if a happens to be equal to b, then there is no area. Delta x is equal to 0. That's one way you can think about it, but also you can think about that there's no area, and so the integral then is equal to 0. Okay, now here's some more properties that will help us in evaluating integrals. So if you have a constant, and this is like the argument, the function is a constant is what they're saying here. F of x is equal to c. Okay, f of x is equal to a constant. Then the definite integral is just the constant times the b minus a. Okay, here they're just saying that if you have the definite integral from a to b of f of x plus g of x dx, then you can separate those out into two separate definite integrals. Here, they're saying you can, if you have a constant times a function, you can just bring the constant out front of the integral. And then here's these two are exactly the same, but this is just with a minus. All right. Now, this first property makes sense because think about this is one of those where you can, we talked about how you can kind of manually evaluate an integral. If you have like the line y is equal to x and you're doing the definite integral, well, just sum up the areas manually because you can calculate the area of a triangle. Well, what is the function f of x is equal to c? It's a constant value. So that's what they're saying here. This is the area of a rectangle. The height of the rectangle times the width of the rectangle, right? If you come here, that's what they're showing here. That this is the integral from a to b where f of x is equal to c. This is just the area of a rectangle, okay? Here's another property. So if you have the definite integral from a to c of f of x dx plus the definite integral from c to b of f of x dx, then that's equal to the definite integral from a to b of f of x dx. And this is what this is saying. So you have the definite integral from a to c of f of x dx plus the definite integral from c to b of f of x dx. And what is that equal to? The definite integral from a to b of f of x dx. Now, the way they have it drawn out here, it makes it seem like, well, this only works if, you have a, b, and c that are positive, but that's not the case. This is the case in general. So a, b, and c can be positive or negative numbers, and it's the exact same result. Like you can't have c is the same number though. Like you can't have c here be -2 and then c here be +2. Then these two c's aren't the same. But like a could be positive, b could be negative, or vice versa, and it's the exact same result. The function could be negative over some regions, it doesn't matter. Okay, so it says properties 1 through 5, the properties we just went over. So these 4 properties here and this property here are true whether a is less than b, a is equal to b, or a is greater than b. They're true in general. The following properties in which we compare sizes of functions and sizes of integrals are true only if a is less than or equal to b. Okay, so these are true only if a is less than or equal to b. Note that. All right. If f of x is greater than or equal to 0, for x is greater than or equal to a, less than or equal to b, then the integral from a to b of f of x dx is greater than or equal to 0. And that makes sense because this situation is it's the area under the curve. If f of x is greater than or equal to 0 for all x within the interval, then you're going to have an area that's either equal to 0 or it's going to be something greater than 0, right? That's what they're saying, okay? If f of x is greater than or equal to g of x for all x within the interval from a to b, well, okay, I want to point out, though, the idea is you couldn't say this is important that a is less than b, because otherwise, like, yeah, this integral is positive, but if you say like but if you switch this to the integral from b to a, then all of a sudden it's negative. So that's why this restriction is important. All right, if f of x is greater than or equal to g of x for x, the interval from a to b, then the integral from a to b f of x dx is greater than or equal to the integral from a to b of g of x dx. And this is kind of common sense too. It's just saying that if you have a function that's always greater than or equal to another function, even if one or both of those functions are negative, then the integral from over that interval of the function that's greater than the other function is going to be larger. And you can this is like common sense based on what we understand about the definite integral. Even if the functions are negative, it doesn't matter, because even if the g of x is way more negative than the f of x, so maybe the magnitude of this integral would be larger, but it's still going to be more negative, so it's going to be less than this integral no matter what. Okay, if f of x is always between two numbers over the interval from x from a to b, and so look at this diagram here. F of x is always less than this capital M and always greater than this lowercase m. They happen to be touching here. M is touching the f of x. M is over the interval, m is the absolute minimum of f of x over that interval, and capital M is the absolute maximum, but that's not a requirement. This capital M could be way up here, but they're just using this as an illustration, okay, for over the interval from a to b. Then lowercase m times the interval width is less than or equal to the actual integral from a to b, which is less than or equal to the uppercase m times the interval width. Yeah, so what they're saying here is that the actual integral, okay, like we know that this integral here, which is this entire area, that's going to have to be, based on these constraints, that's going to be greater than or equal to this area. Greater than or equal to. And The actual definite integral is going to, no matter what, be less than or equal to this area. That's what they're saying, okay? Okay, and just note, though, these properties were strictly for when A is, the limits of integration, A is less than or equal to B. But these properties, okay, and this property were true no matter what the situation. A is less than B, A is equal to B, A is greater than B. Okay, so that's the definite integral.